recorded that. We're going to go now to talk about the other thing I asked you to do, which was I asked you to create a separate version of the first order delay, where instead of creating it simply as a flow in and flow out, we actually had it following a target. Can anyone tell me how they attempted to do this? How did you attempt to pursue that? Anyone? So here's an original first order delay, right? And I'll actually go open the one I think we built together last time, and I'll do it here. First order delay model 2. Here we go. So, ladies and gentlemen, how would that be different from this? Well, yes.
The equation for the inflow,
Mm-hmm.
the one you had us do,
Mm-hmm.
incorporated the target.
Good.
This one was
Good.
kind of equilibrium kind of hit.
Yeah, so it reached equilibrium. There was some target here, but it was somewhat implicit. There wasn't an explicit target. What is the target here of the outflow?
10? Or
Yeah. So let's suppose the inflow is fixed. Let's say at 10. What's the target of the outflow? 10. Remember, these stocks are self-governing systems. They exhibit a balancing feedback. They seek a state of equilibrium. It's a negative feedback. They seek a state of balance, of stability. And at that state of balance, what is the outflow? It's 10. Yeah, it's the same as the inflow. Good. Now, what is the value of P? What's the target value of P? If we phrase it this way. P divided by alpha. That's right. That's exactly right. So P tends to go to a target, but it's a little bit implicit here. Ladies and gentlemen, let us change that. So what we did is, this was target-based formulation, right? First order delay model, target-based formulation. And what did we do? What did we do here? Well, ladies and gentlemen, what we did was a little bit of kind of shuffling, but mathematically it wasn't anything too deep. Yeah. Sometimes I like, when it comes to future versions of the course, to be able to capture some of the informal props I used that students found helpful. So I'm just going to take photos of these so I can, so that future students will enjoy a bequest from some of these discussions. Okay, so let's get rid of this and let's talk about what we're doing here. So here we have a flow, and we have an inflow, and we have an outflow. The inflow, let's say, is I, and and here we have X. And I'm going to phrase it in terms of tau. Oh, look, there's a tau already up there. Reuse. Okay, great. So what's the formula for this?
Like x times tau is x divided x over tau.
Okay, X over tau. Why do we know that? Because it was a good call, and I welcome people trying things. Tau here is measured in time. And so this has got to be persons per unit time if this is persons. So it's got to be over, not times. Otherwise, this would be person times, like 100 person years, which isn't what we want. Okay, so it's alpha over tau. Ladies and gentlemen, as Francis Bacon said, truth is easier obtained from error than from confusion. It's better to try something, try an idea out, suggest it, than to sit there puzzled and not saying anything. So I view attempts, whether correct or not, ultimately as extremely good contributions to this class. So this is, it turns out, X over 2. And let's talk about reformulating this. So suppose So I would argue here that dx dt, the rate of change of x, is equal to what? I told you it's the net flow, right? So what's the net flow here? Inflow minus outflow, right? There we go. This is the rate of change. If we have 10 liters per minute coming in, and let's suppose right now 5 liters going out, the rate of change, the amount of volume of water in our tub, is going to be 5 per minute. That makes sense? It's going to be rising at 5 per minute. Yeah? Okay, good. So that's the rate of change for the volume of water of the stock. Okay, so I could rewrite this with one flow. I don't need 2 flows for this. I could rewrite it as one flow. So I could take this and I could just have one flow coming in. Here's x. And what would the formula for this flow be? Well, this could be one flow. I could put this all in one flow. Give me the formula for this flow. I minus x over tau. Great. Great. I minus x over tau. That's the same thing as that mathematically. It's exactly the same. But, ladies and gentlemen, I'm going to engage in some rewriting. So, suppose I don't like having divisions in my formula there. Suppose I don't like having this over tau. What could I do to get rid of the division that's in place there? Suppose I wanted to just have it as 2 factors. Well, I could replace this by, I'll write it above it so you can see the equivalence. I could write this as minus x. I could write as I times tau minus x all times 1 over tau. Okay? Right? You see the equivalent? This tau cancels that one, and this goes to that. You see that? Okay. Now, that's all well and good, but what's I tau? Does anyone recognize this? Let me rephrase it to try to point this out. This is our friend. Okay, no, some of you may think it's your enemy. But, sorry? It's the target. It's the target. It's the equilibrium value of the stock. To rewrite this, what's the relationship between tau and alpha? Anyone remember? 1 over. So how can I rewrite this in terms of alpha? If it's I times tau, it's I divided by alpha. Do you recognize that? Ladies and gentlemen, that's the equilibrium value here. The outflow was seeking the value of I, right? It was seeking the value of I in a first order delay. What is the value of x for which the outflow will have that value I? What does x have to be? What does x have to be such x divided by tau? If we want the x for which x divided by tau, in other words, the outflow equals the inflow, what does that imply about what the value of x is? Okay, so, ladies and gentlemen, we're seeking a value of x, a value of the stock for which the inflow equals the outflow. X over tau equals inflow. So what does that imply? What's the value of x? I times tau. I times tau. That's our I tau. That's our I tau here. Ladies and gentlemen, that's our I tau. We could call this, you could just name, this is some constant. It's some value of I, some value of tau. We could call it target. This is just some number. It's our number. And we're going to call it the target because it kind of makes sense. Target over tau. So in other words, ladies and gentlemen, this is, I'm just sort of rewriting this as that. So this could be written as alternatively target, some target, minus x over tau. Now, intuitively, what's target minus x? What is that? What is that? That's Yes, it's the gap value between target and x. It's the discrepancy between them. If target is bigger than x, what does x need to do? Needs to increase, right? So there's going to be inflow as a result, right? So in other words, if this inflow has a rate associated with it of target minus x over tau, the bigger the gap is, the more target is above x, the bigger that numerator is going to be, target minus x. So the bigger that divided by tau is going to be, and therefore the more flow into x is going to be. And so x is going to be going, there's lots of flow in. There's no flow out here anymore, ladies and gentlemen. We put them all into the inflow. So the bigger that is, what's going to happen to x? If target is way above x, if target is 1,000,000 and x is 0, what's going to happen to x? It's going to grow, right? And if suppose tau is 1, man, this thing is going to be 1,000,000 minus 0 over 1 is going to be 1,000,000. dx dt equals 1,000,000. 1,000,000 liters per minute are going to flow into your back. No, don't mention that. Okay, ladies and gentlemen, so x is going to shoot up, right? If target is the same as x, what's x going to do? Stay the same. The inflow will be 0. If x is on the target, it's going to stay on the target. Suppose target is below x. What's going to happen? Don't worry, you can have a net flow in that's negative. So what's going to happen? It's going to be going down. It's going to be flowing out, essentially. Yes, it's shown as an inflow, but if it's negative, it's a net outflow. And so it's going to be going down. Target is way below x. If x is 1,000,000 and target is 0, it's going to, and tau is 1, it's going to be dx dt, the rate of change of x is going to be minus 1,000,000. It's going to be dropping like a rock. Okay, so ladies and gentlemen, here x follows the target. Do you get that? This is the same thing, ladies and gentlemen, as this. All we've done is kind of consolidated things, and we've semantically chosen to associate the name target with I times tau. But it's the same system. It's the same first order delay. But now we can kind of appreciate it in a new way. The value of the stock, over there, we were talking about the value of the flow following the inflow, right? This was a delayed version of the inflow. Over here, we're talking about the value of the stock following whatever target is. It says, okay, I'll follow you, and I know your model doesn't always say it in that stentorian voice, but it'll follow this target, right? But it follows it with a certain delay of tau. It follows it with a certain delay. There's a delay associated with it. And now, ladies and gentlemen, the chickens will come home to roost. Okay? So we're going to see the implications of that. Ladies and gentlemen, what sort of feedback is associated with a first order delay? Negative or positive? Negative, indeed. It's a balancing feedback. The bigger x is, the bigger the outflow is, which will tend to make x smaller. So if x increases, it'll trigger an increase in the outflow, which drags x down. So drags it down below what it otherwise would have been. Same thing here, right? There's a negative feedback here. If x is equal to the target and we increase x, guess what will happen? This will go negative. It'll drag down the value of x. If x is pushed below target, if it's pushed down below target, target minus x will be large, and it will be larger, and therefore there'll be net inflow, and so it'll bring x up. This is a negative feedback system, right? And we saw that it leads to stability, right? We saw that it leads to this kind of situation where it bounces back. And ladies and gentlemen, I hope that you experimented in your with your model, reformulating it in these certain ways. So, here we can get rid of these things, right? So we can get rid of outflow, and we can get rid of this. And we're going to go put this over here, and we can drag in a target here. Here we go, a target. This is target. This is a target for what? It's going to be a target for the value of the, of the stock. Good. Okay, ladies and gentlemen. So here we're going to have it. And what else do we need besides the target? We need a mean, this is like delay. You could call it delay. We're not really thinking of it as mean time in the system right now. It's kind of a delay associated with following the target. And here we have P. It starts at 0. We're going to have target. Its default value will be let's say 10. Okay. And here we're going to have the inflow be. We're going to have the inflow be what? Give me the formula. It sits on the board behind me, but you should be able to tell it to me. What is the formula for the inflow here? Target minus P divided by delay, right? Thing of beauty. Okay, so ladies and gentlemen, let's play around with this a little bit. Oh, outflow cannot be resolved. Why is it? Oh, I know why. It's because the graph above refers to outflow. Okay, time to remove that. Time to remove the outflow. Here we are. And boom, dead. Okay, ladies and gentlemen. There we go. And let us now, okay, now unfortunately I sort of removed the variable that was frobbed by all of these things. So really we should rename these, but in the interest of time, I'm going to run this because I want to get to one final major point here. Here's the first order delay model, and oh my gosh, oh man, yeah, delay is 0. Sorry folks, I should have told you. Delay, the default delay value we'll make it 0. Okay? Great. So very good. That's for the, actually, I'm sorry, make the default one, make it 10. 10.0 for the delay as well. Make for the high, well, if you have a high leaving hazard, we could change it, but let's just do it interactively. Okay? So I made it 10, and we will modify it manually. So here we go. Here's our model, and here we go up here. Now I'm going to modify this delay to be. So notice, by the way, this is coming along. What is P tending towards? What value is it tending towards? The target. Value of 10. So let's make the target, let's make it 5. What's going to happen now? Hey. What's oh. Sorry, that was the delay. What am I doing? Sorry. I'll have it known, ladies and gentlemen, that yesterday I spent the day talking to a conference in Toronto, and my key thing is I didn't want to miss this class either this morning or 2 days ago. So I got up at 4 yesterday, flew to Toronto, went to the conference, gave my session, took in a few more sessions, and then I flew back last night, and I got back about midnight. So it was not the most fun day, but it was all for your sake, honestly. Also, I could be here these 2 days. I did not want to miss it, and I hope neither did you. Okay, ladies and gentlemen. So let's change the target now. Let's have this go a bit slower. We're going to change the target to be 5. Okay, 5. Okay. So if I'm not in my finest form today, it is for good reason. And I hope you'll lend me a bit of sympathy. Okay, so let's take it up to 15. And now it's following this target, right? And we're going to take it down to 2. It's following the target, but with some delay. Now, suppose that delay were smaller. Suppose we were to start rerunning this, but with a very small delay. Let's make the delay 1. What do you think the impact will be?
Because we have a steeper curve.
Yeah, we're going to have a steeper curve. It will more quickly adjust, right? So let's change the target, for example, to be 5, and you can see it very quickly adjusts to the target. 3, very quickly readjusts. So here it follows that target very quickly. Okay, now, ladies and gentlemen, I want to, in the final moments here of class, I want to take this model and I want to save it as, and I'll get you started on something that you may have to finish in your take-home exercise. And this will be called coupled first-order delays. Okay? Both of them are going to have a negative feedback associated with them. Ladies and gentlemen, you're going to copy this. And so you're going to copy this one. And the best way I'm going to do it, just so we're not aesthetically handicapped, is I'm going to copy it, and then I'm going to press Control. Okay, I was hoping to do Control drag on it, so it would drag it down and copy it at the same time. There we go. Okay, so I grabbed it and I held down Control on my computer, maybe Option on Macs or Command on Macs. I'm not sure which, but you select the whole thing and you drag it while holding that down, and it can copy the whole thing. And the key thing here, ladies and gentlemen, is going to be the following. P1 is going to be called perceived P. Okay? The delay for the bottom one is going to be called perception delay. And ladies and gentlemen, instead of having a target 1 here, instead of that being a fixed value, this, ladies and gentlemen, is going to be the value of P. So in other words, perceived P is going to track P, but with some delay. Do you see that? So this perceived P, which if you folks are having trouble, you could even recreate, it's going to track P as the target, but with some perception delay. In other words, this did go in, this link here went in from target, now it goes in instead from P. P is serving as the target for the perceived P. Not only that, we're going to make one final change here. Ladies and gentlemen, we are going to have perceived P serve as the inflow rather than P itself to the inflow to P. Okay? So, how is that? Well, in other words, P is going to be adjusted to follow the target, not based on the true value of P, not the true value of the underlying system, but based on the perceived value of the underlying system. Your perceived grade in the course, your perceived level of blood sugar or of hunger, your perceived level of risk to the company. Ladies and gentlemen, often, and this relates to Mac's question earlier, often we relate to the world not in terms of the true state of the world, but our perception of it. This may be our perception of the car's angle when we're trying to drive on ice, the angle of the tires or what have you. So here, perceived P will be used here. The inflow for this top one now will not be target minus P divided by delay, but target minus what? Perceived P. And, ladies and gentlemen, the inflow here, down inflow 1, the inflow for the lower one, will be based not on target minus P, but on P, because P is serving as the target for this lower one, minus perceived P. Okay?
Do we want to change delay to perception delay as well?
Up here? No, because this is
Inflow 1.
sorry. So, yeah, it should be over perceived delay. Thank you very much. Perception delay. Perception delay. You're absolutely right. Yeah. Okay, ladies and gentlemen. So we have two first-order delays coupled in this kind of reformulated way. So for the top one, what is it trying to track? What is it trying to follow? Target, with a certain delay to undertake action to follow it. But it doesn't have perfect knowledge of the true situation. Instead, all it has is the perceived value of this. And it's going to and that's going to depend on perceived P. Perceived P is going to track P, but with some what? Perception delay. And it is perceived P that's going to be used up here. Who would like me to show one of these formulas? Anyone? Who would like me to show one of them? The top inflow is going to be target minus perceived P divided by delay. It's not going to, in trying to follow the target, it's not going to know the true value of P. It's just the perceived value. The bottom one, the formula for it is going to be P. That's going to serve as the target for the bottom, minus perceived P, the gap between the true and the perceived one, over the perception delay. The longer it takes to perceive the delay, ladies and gentlemen, the bigger the gap will be between our perceived value of P and the actual P. And that's going to be operationally. So I'd invite you now to run it. Okay? So here we are. Here we have this thing going. And what are we going to see? Before, ladies and gentlemen, we saw a convergence to a value, to a single value. What do we see now instead? Not quite the neat convergence that we used to see. What do we see instead? It's overshooting, ladies and gentlemen. Overshooting because the perception of it is not caught up. Okay, that's great. I would ask you to play around with this. How, as the perception delay changes, does this change? Let's change the perception delay from 10 to 50, for example, right? You can do it in a different scenario. How is this going to be different? Well, now we're going to see multiple oscillations here, okay? How if as we change delay, how would that change things? Try playing around with different versions, different values of perception delay, and you will recognize that there's actually a fair bit of dynamics here that depart from our classic little case of convergence nicely to some stable value. Rather, they start to elicit some considerable oscillations, okay? So I'm going to do a perceived delay of 5, but a delay in changing the situation of 2, for example, and you should be able to see some pronounced dynamics. You'll notice eventually it seems to converge. Eventually, as we drive that car on the ice and it's going this way, and we overshoot and we come back and it's going that way, and our perception is off, eventually we often straighten out and go forward. We stop that fishtailing. But this captures the effect of perception. And ladies and gentlemen, those of you who are computer scientists who aspire to work in the IT sector, be aware that IT has a huge impact on perception delay when it comes to organizations. How quickly managers have access to data about how the organization is doing, how sales are doing. How quickly we have access to understanding of our health state has a big impact on how quickly we can put in place corrective action. How quickly you can get feedback on marks or what have you has a significant impact on your ability to correct. So this system, while very stylized, P and perceived P, it points to an underlying truth that when you have a corrective system, a system that has a balancing loop that tries to correct for the situation, to bring us back into equilibrium, that system can be jeopardized if there are long, in its effectiveness, if there are long perception delays associated with perceiving our current situation. In that case, we can have these kind of oscillations where things kind of kick around for a while until we can finally settle down to values that get closer and closer to the real situation. And there's a lot of situations in the world, ladies and gentlemen, where oscillations are caused in the business sector, for example, because of this effect. And IT is changing that by shortening some of that perception delay by allowing just-in-time summaries of things in ways that can have real implications for volatility. But it can also cause other types of volatility. So perception delays, ladies and gentlemen. 2 coupled first-order delays, each with sort of balancing components coupled together, you can get some very different behavior associated with oscillations. So I'd like you to explore that a little bit, and I will look forward to seeing you. I'm going to hold office hours, as will be my practice from now on, and 3:41. Through there, we had good attendance last time, and I would welcome students this time as well. And I know I'm meeting several of you on projects shortly as well, and we're continuing to have those meetings. Thank you very much.